Hello and welcome to today's lecture. So, we will continue from where we left off in last lecture. We were discussing we had discussed the relative advantages and disadvantages of computing metrics of mean, median and mode, and then we went on to starting to discuss ways and means of quantifying the dispersion in the extent of dispersion in the data. So, just a quick recap between mean, median and mode. So, as you know, mean is much more sensitive to the presence of outliers in the data. Mode is of course not sensitive, median is also not sensitive. Mode is primarily used while describing large sets of data, while mean and median can be used for describing both small and large sets of data, right. So, but as we discussed that if you have a population like this, so this is x and this is your frequency. So, just computing one value as mean or median or mode is not sufficient. There has to be a way of capturing the dispersion in this data, and there are various metrics for computing this. The most simplest is the range, and range is nothing but essentially defined as the maximum and minimum of this data. Okay. So, as you can clearly see in this case, the minimum is 40, the maximum is 100. So, the range is 60. So, as you can also see that in this case your value, so range has to be thought of in the context of the minimum or the maximum or the average. Okay. So, you can have a value of 1, it will not change your maximum, but will drastically change the mean. So, you have to think of range in the context of what is the minimum and the maximum value. We then discussed about standard deviation. So, standard deviation is essentially the sum of the squares of x values from the average, either the population average or the sample average. The notable difference is after you add them up, you square them up, you add them up. So, it does not matter whether the value was lesser or greater than particular average, and then you divide by the total number of observations in the population. But in case of calculating the standard deviation of a sample, you divide by n minus 1. So, this is the most important difference between these two cases. We then came to this, we had derived this expression that when you do this xi minus x bar whole square, you can, this is as good as exactly the same as calculating this particular term, which is summation x square minus n times x bar square. So, let us just take this particular example and see whether this holds good or not. Okay. So, let me write down the values of xi minus x bar. So, xi is 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. My x bar I can calculate as, so 2 is going to be 12 plus 12 plus 12 plus 12, 48, 54 by 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is equal to 6. Okay. My x bar is 6. So, I will plot two terms, x square and maybe xi minus x bar whole square. Okay. So, this is 4, xi minus x bar is 4 square is 16, 3 is 3 square is 9, 4 is 2 square is 4, 5 is 1 square is 1, 6 is 0, 7 gives me 1, 8 gives me 4, 9 gives me 9, 10 gives me 16, and for x square is 3 square 9, 16, 25, 36, 49, 64, 81, 100. Okay. So, I have to add up all these x bar squares. So, let us see what this gives us. 13 and 16, 29, 29 and 25, 54, 54 and 36 is 90, 90 and so you have 90 plus, okay, this is 90 plus 49 plus this is 145 plus 100. Okay. So, which is 90, so 194 to 384. So, summation x square. So, summation x square is roughly 384, and summation xi minus x bar whole square is 25 plus 4 25 plus 4 29 30 31 plus 35 9 44 60. Okay. So, I know this value. So, let me again write it down here. My x square is 384 and my summation xi minus x bar whole square is 60. Okay. So, this is 60. Now, summation x square minus n times x square average is equal to 384 minus total number is 9 into x bar is 6 so square. So, 36 and 9. So, 36 into 9. So, 36 into 9 is 9 6 54 324. So, this is 384 minus 324 is equal to 60. So, just this and this is the same. We have confirmed these two values are the same. Now, of course, when you are doing it by hand, it does not have any value in doing this. In that case, doing the x pi minus x bar route is easier, but in while you are doing these calculations in a computer by writing a program, this is much more advantageous. Okay. So, we then discussed about transformations. So, we had come. So, if you have y is equal to a x, then you can have s y will simply be a times s x. If you have y is equal to c plus x, s y is simply equal to s x, and in the general case when y is equal to c plus a x, s y will still be equal to a s x. So, bottom line is when you have a prefactor which multiplies your variable x to generate your variable y, then that also gets reflected in the standard deviation calculation. But when you have a constant being added, it has no contribution to the variation. So, let us think of the practical significance of your data, of what the standard deviation tells us. Okay. And that brings us, so let us say if this is your data, okay, x and frequency. Okay. So, we want to know, so let us just say that this is your mean and you have a standard deviation. Okay. So, let us say this may be your standard deviation. Okay. So, we want to know what this standard deviation conveys. So, one theorem I will turn to, it is very important, it is Chebyshev's theorem. So, what it states, given a number k greater than 1 and a set of n measurements, at least 1 minus 1 by k square of the measurements will lie within k standard deviations of their mean. So, what it tells us is if you have mu, okay, or if you have x bar as your mean, then x bar plus minus 1 times mu. So, if n is or plus minus 2 times standard deviation will contain how much of the population? 1 minus 1 by 2 square is equal to 3/4. So, 75% of the population will lie between x bar minus 2 mu and x bar plus 2 mu. 75% of the population will lie between x bar minus 2, sorry, this is sigma 2s. So, this is just a standard deviation s. Okay. So, 75% of the population will lie between x bar minus 2s and x bar plus 2s. Okay. Similarly, if you put k is equal to 3, then x bar plus minus 3s, you have the value 1 minus 1 by 3 square equal to 8 by 9, which roughly is 90% of your data will lie between 3 standard deviations of your population. So, this is Chebyshev's theorem. Let us test it with the following example. So, you have these values, okay, 26.1, 26, 14.5, 29.3. Okay. So, so before we go this, I think I skipped this value. So, let us come to this example. So, imagine you have 26 observations and the mean of the population is 75. Okay. So, you have n is equal to 26, x bar is equal to 75 and variance equal to 100. So, standard deviation is equal to 10. So, it tells that if n is equal to 26, then so between x bar plus minus 2 times standard deviation, which would mean that 75 plus minus 20. So, between the values 55 to 95 you will have 3/4 of the population, that is equal to 3/4 into 26 observations will actually be within this range. Similarly, x bar plus minus 3 standard deviation would give me 75 plus minus 30. So, between the number 45 to 105 you will have 8 by 9 into 26 number of the population will lie within this number. So, this allows us to think of how much of the data will represent bulk of the data, how much of the fraction of the population represents bulk of the data. Let us test this particular example as well. So, you have the following population and you can calculate the mean of this population to be roughly 22. So, the number of observations are 1, 2, 3, 4, 5. So, in this case n is equal to 15, your x bar is equal to 22. So, let us say, so it what Chebyshev's theorem predicts is between 22 plus minus 2 times the standard deviation. Okay. So, we have not calculated the standard deviation. So, let us see. Okay. So, you have 26.1, 26, 14.5, okay. So, we have to calculate the standard of deviation for this particular problem. I will leave it to you to do it, but you can test. So, you can find out. So, you calculate the standard deviation, step 1, calculate x bar plus minus 2 times standard deviation and check. So, this is my, and step 3, check if this theorem is true. So, for distributions which are different than Chebyshev's, but many times you obtain mound like distributions. So, where there is a clear peak, there is a tendency for the data to accumulate towards the center of the distribution. This is a mound type of distribution and very often the term normal distribution is used. So, for these kind of distributions what is known is within one standard deviation of the data 68% of the data is there. Within 2 standard deviations of the data 95% of the data is there, okay? And within 3 standard deviations of the data 99.7% of the data is there. So, you can see that compared to what Chebyshev's theorem predicts, which is that within 2 standard deviations you have 75% of the data. So, this clearly tells you that Chebyshev's theorem is a much more conservative estimate. That means, it underestimates how much population is, because it makes no assumption as to how the population is distributed. But for these particular normal distributions, you see that instead of 75% predicted by Chebyshev's theorem, 95% of the population falls between plus minus 2 standard deviations. So, this brings us to a very good exercise that, so for all practical purposes you can consider 95% of the data to be the entire data itself. Okay. So, when you calculate standard deviation, right, you can to check whether the value of standard deviation that you have calculated is approximately is right or not. The exercise is very simple, you calculate the range, right. So, what normal, in case of normal distribution, okay, in case of normal distribution x bar plus minus 2 standard deviations is 95% of the data. So, which we can approximate as 100%. So, if this is 100% of the data, that means the difference. So, x bar plus minus 2 standard deviation will simply be is equal to the range. So, the range will give me the 2 extremes. So, this would mean that roughly my 4 standard deviation is equal to the range. Okay. So, that is a very easy way to test. So, let us take the following example. Let us say if you have 5, 7, 1, 3, 4, right. My range is equal to maximum minus minimum, 7 minus 1 is equal to 6. Okay. What is my standard deviation? My average is, so my x bar is 5 plus 7 plus 1 plus 3 plus 4 divided by 5, 12, 13, 16, 20. So, x bar is 4. So, my standard deviation is equal to square root of, so 5 minus 4 1 square plus 7 minus 4 3 square plus 1 minus 4 3 square plus 3 minus 4 1 square plus 4 minus 4 0 square, right. By 1 2 3 4 5 you have square root of 4 is equal to square root of, so 9 plus 1 10. So, 10 and 10 20, root 20 by 4 is equal to square root of 5, which will give you a value of 2.2, right. So, your range is 6, your standard deviation is 2.2, that means that 2.2 into 4 is 8, they are comparable. So, you know that this kind of is probably right, okay. But if you had gotten a value of standard deviation as 10, that would have surely told you that there is something wrong in the calculation. So, this is this is not exact, but it gives you a way of testing whether the value you have calculated is reasonable or not. Now, when we are handling biological data, right, let us say you do an experiment where you measure how fast cells move, you have huge heterogeneity in the data. So, your error bar is going to be humongous. So, one way of reducing this error bar, of plotting the error bar, is not by plotting the standard of deviation, but by plotting the standard error of the mean, and the standard error of the mean is defined by sigma m is equal to sigma m by root of n. So, sigma is the standard deviation, you divide by square root of n. So, this clearly tells you when your n increases, then sigma m will decrease. So, if n is 4, for example, sigma m will be sigma by 2, half of sigma. If n is 100, then sigma m will be sigma by 10. So, your standard error bar will decrease, but again this is a measure, this tells you how confident are you of calculating the mean, okay. So, one more thing which is very important is the concept of z score or relative scoring, right. Imagine a class of students have taken an exam, and always you want to know how you are positioned with respect to the entire population, or how you have performed relative to how the class has performed. And z score, so z score is defined by, for given score x minus x bar by standard deviation, okay. So, z score is defined by this particular example. So, if we take this example, if my mean is 25, my standard deviation is 4, then if x is equal to 30, so I get a z score of 30 minus 25 by 4, which is roughly 1, okay. 30 minus 25 is so it's actually 1.25, is equal to 1.25, but for all practical purposes which is roughly 1. So, one thing, so the z score gives you a way of testing whether a particular value is an outlier or not, and this is an empirical in nature, but what is considered is if your z score is greater than 3, then that particular value is an outlier. Let us take the following example, okay. So, you have these values, so your data is 1 1 0 15 2 3 4 0 1 3, right. So, for this particular value the z score, okay, so we of course have to calculate the x bar, okay. X bar is 2 plus 15 17 20 22 26 30 3 4 5 6 7 8 9 10, okay. So, x bar is 3, standard deviation, okay. So, in most of the cases it will be 0. So, your standard deviation will be let us say ordered 3, then my z score of 15 will give me 15 minus x bar is 3 by 3 is giving a value of 4, but I think the standard deviation will probably be order 4 or higher, 5, okay, in that case. But what you can clearly see is with this calculation, it may not be an exact calculation, but in this case your z score of 15, just by looking at the data, when you see most of your points are within 5 or 4, and then this 15 value is sticking out, then you know that this is really an outlier, and one way to do it is to calculate a z score and see whether this value is greater than 3. If it is greater than 3, you can completely remove this value, and then recalculate your statistics. So, this helps you to remove outliers which completely mask the information that is contained in your data. Another important metric which is widely used is the concept of relative standing or percentiles, right. A pth, so the definition of a percentile is as follows: a pth percentile is the value which is greater than p% of the measurements. Okay. So, you can have, based on that, you can have first quartile which is at position 25%. So, it is defined is the first quartile is the value which is positioned at position 0.25/n+1. Accordingly, the third quartile is defined at position 0.7 times at n+1, and you can calculate something called the interquartile range, which is nothing but the difference between Q3 and Q1. So, again let us take the following example. So, you want to calculate the quartile. So, you have the following example: 4, 18, 11, 13, 20, 8, 11, 9. So, first thing will of course be sort 4, 8, 11, 11, 13, okay, 16, 18, 20, 13, 16, 18, 20, 25, 1, 2, 3, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10. So, 4, 8, 11, 13, 11, 11, 13, 16, then you have 18, then you have 20, then 25. Okay. So, let us say you have the following measurements 1, 2, 3, 4, 5, 6, 7, 8, 9. So, you have total of 9 numbers. So, for calculating Q1 you do 1/4 into 9 plus 1, okay, which is 2.5. Okay. So, it tells you, so 2.5 is middle of this 8 and 11 number. So, for calculating Q1 you have to do 8 plus 0.5 times 11 minus 8. So, this is how you will calculate Q1. Okay. For calculating Q3 we need 0.75. So, 3/4 times 9 plus 1 is equal to 7.5 position, right. So, for calculating Q3, so what is the 7th position? 1, 2, 3, 4, 5, 6, 7. So, 7.5. So, this is your Q3. So, it is going to be 18 plus 0.5 into 20 minus 18. Okay. So, this is how you will calculate Q1 and Q2, and in Q1 and Q3. So, Q2 is nothing but your median. Okay. Q2 is nothing but your median. So, this is another example. So, where you can calculate the same thing, but I am not going into the details, but essentially the same thing. You ordered them, you find out what is total number of measures, you calculate which point is where, and then n, you find out the position and you have to interpolate. So, depending on, if let us say hypothetically between these two numbers you get a value of position as 2.25, then you have to take the, and this is position 2, this is the next position, you have to take this position and then 0.25 times the following 2 points. So, what these these quartiles, once you calculate the quartile, one of the way of representing data is using what is widely used, is called a box plot. So, this is how a box plot looks. Okay. So, this value, okay, so you have this entire range within which you have this value is your median, the square value. So, the square value is your average, the square value is your average, this is your median, this is your maximum, but this is your 75. So, third quartile, this is your first quartile. Okay. First quartile, median, third quartile, this is the maximum and this is the minimum. But what you can see is these error bars do not always extend to the maximum or the minimum, because you calculate what is called as the lower fence is defined as Q1 minus 1.5 times interquartile range and Q3 is defined, upper fence is defined as Q3 plus 1.5 times interquartile range. So, when you plot, so for example, in this particular data set, what you said, even after you have done that, there is this point which is a clear outlier. Okay. But for this case, the extreme point and where your your error bars extend is the same point. So, this would convey that this point is not an external point. Okay. So, in this case also you can see the error bar here, you can see the error bar here, which conveys the message that this point is an outlier. The other thing I wanted to look at here is the square point, which shows the mean position. So, what you see is in both these cases of the data, your mean and median are very close to each other. Okay. While for this data, for example, the mean is biased towards the upward side. So, this would mean that you have less number of values which populate this portion of the data and greater number of values which populate this portion of data, because of which this is higher. So, when you have the same thing, when your population is not outside the outlier, as in this case of this case, so your minimum and the error bar would kind of converge. But in these cases, in this case here or in this case here, these points are clear outliers which which lie much outside the bulk of the data. So, that is how you can detect outliers to find out where is your lower fence, where is your upper fence, and then calculate what is your how you want to plot your box plot. So, let us take a sample data set, let us say. So, we do 1, 2, 3, 8, 10, 12. So, this is your data set, right. So, your n is equal to 1, 2, 3, 4, 5, 6. So, your q1 is at position. So, position is 0.25 star 6 plus 1 is equal to 7 by 4 is equal to 1.75. So, my q1 is 1.75 position. So, between 1 and 2 it is going to be 1 plus 0.75 times 2 minus 1 is equal to 1.75. Okay. This is the position, remember. Okay. Now, for q3 you have position is 0.75 times 6 plus 1 is equal to 3/4 into 7, okay, 21 by 4, which is 5.25. So, fifth number is 10th, okay, but only you have 0.25. So, q3 is equal to 10 plus 0.25 times 12 minus 10 is 2. So, is 5. So, 2 into 0.5. So, 10.5 is your q3. Okay. So, my IQR is equal to q3 minus q1 is equal to, so 10.5 minus 1.75 is I think 8.75. Okay. IQR is 8.75. So, as per this, my lower fence has to be q1 minus 1.5 times IQR, right. So, my lower fence is q1 minus 1.5 into 8.75 and upper fence q3 plus 1.5 into 8.75. Okay. So, you can, I think none of these points will be outside the range. Okay. So, most of these points will lie inside your plot, and your box plot, if you plot, will probably look something like this. And so, your median and your median, since each of these values are only repeated once, your median will be in between, your mean and median will be very close to each other, and your error bar won't, your error bar will encompass all the points, because none of the points lie outside. Okay. So, but it is possible to have plots where your, let us say you have an error bar like this. Okay. So, where your this point is way outside the maximum to which this goes, this is your upper fence, which is q3 plus 1.5 times IQR. With that, I complete here. So, essentially we have discussed how to calculate standard deviation, and then from that how can you, based on mean and standard deviation, how to get an idea of how much of the population lies in the bulk and how much of these points are outliers. So, using z-score you can get an idea of which point is an outlier, and using box plot you can represent the whole data to show how it looks. So, it of course conveys the message which of these points are outliers or not. With that, I thank you for your attention. We will meet again in the next class. Thank you.